Hello and welcome to part 2 of module 18 in our C language series. Today we're going to focus on the binary tree approach to sparse arrays. Let's begin with the question. Could we call the binary tree a modified linked list? And if we think about the question, as well as the structure that we used with the linked list, we have two pointers there, one pointing to the next node or the link in the list and one pointing to the previous. And as you may have figured out, this is a doubly linked list. Now, when we talk about the binary tree and the structure that we're going to use for that sparse array is going to be something like this. And as you can see again, we have two pointers, one pointing to the left node and one pointing to the right. And so you can see that the binary tree is in effect a modified version of a doubly linked list, right? What then is the advantage over a list? And as we've seen from our previous discussions on binary trees, a binary tree allows for quick searches, which in turn allow for fast insertions into the tree as well as fast lookups, right? Now, the best way to understand the binary tree approach to sparse arrays is, of course, to write code. So we're going to write code that will use a binary tree to implement a sparse array. The program should mimic the feature of a spreadsheet so that the cell should reflect the calculated result of a formula. If the formula begins with an equal to, the cell should otherwise reflect the formula as a string. For simplicity, restrict the formula to two operands only and restrict numbers to single digits for this program. So let's now go to code blocks and we can start a new file. And we start with hashtag include stdio.h and hashtag include stdlib.h. Remember, we need malloc, and then hashtag include string.h. We have our struct node, and that's going to have members char cell name of 9 bytes and char formula of 128 bytes and struct node star left and struct node star right. And call this tree entry. Right, so that's our structure. Then we need some variables. So struct node star root and struct node star rt. And then we have struct node star make tree, which is the function to build the tree. So struct root, or rather node star root. There's going to be one parameter. Struct node star rt is another. Struct node star new cell. That will be the new cell that's going in every time we want to add a node to the tree. Then we have a print function. So void print tree, and that's going to take struct node star rt. And finally, we have int calc formula. That's going to take just the string FMLA or the formula that the user inputs, right? And of course, return the result of that calculation. We have our main function now. And within that, we need some variables. So char row name, which will be used to take input from the user in terms of the row name, and int column number. Again, to get input from the user, initialize root to null and initialize rt to null. Remember, pointers are best initialized, right? Then we have our loop, an eternal loop there. And within that, we have struct node star ptr1. We have int calc result, which will be used to get the return value of this function. Okay, and then we have rt equal to root. Right, so within the loop, every time rt is initialized to root, and now we can use ptr1 with malloc. So ptr1 equal to struct node star and then malloc size of pre-entry. Right, then we check if malloc returns a null, and this should be ptr1. Right, so if not ptr1, which means malloc returned a null, then you know what to do. Printf out of memory and exit 1. Right, otherwise printf enter row and 0 to quit. And then of course scanf %s comma row name flash stdin. Then we check if row name of 0 equal to a 0, then we break out of the loop. Right, otherwise we ask for the column. So printf enter column number and then scanf %d comma ampersand column number. Right, and flash stdin. Then we check if column number is less than 10. Then just as we did for the linked list sparse array, sprintf, and that's going to go into ptr1 cell name. Format command will be %c, %s first, right? %c, %t, and then in order we have row name, that's the %s or the string, 0 for %c, and column number for %d. Else sprintf ptr1 cell name, format command will be %s, %d, and then in order row name and column number. Right, then the next thing we do is enter the formula. So we need to ask the user. So printf enter a formula and then scanf %, that's going to be %s comma ptr1 arrow formula. Right, then flash, of course, if now not root, which means we have an empty tree, then root equal to make tree, and we send in arguments root, which will be null, rt will be null again, and ptr1, right? So after this is executed, we will have a root, right? Otherwise, just call make tree, passing in root, rt, and ptr1, right? And now this completes our while loop. After this, we check if root is not equal to null, then we'll call the print tree function, and we send in the root as the argument. We need to exit the program, so here we will say exit 0, right? Now this bracket is for main, so we have an extra one here which can just be deleted, right? So that completes the main function. So now let's write the code for the make tree function. As we know, it returns a pointer, so struct node star make tree, and the parameters will be struct node star root and struct node star rt, and then of course we need struct node and the new cell. The first thing we do, of course, which you will know by now, is to check if rt is null. So if not rt, new cell left equal to null, right? And then new cell right also equal to null. Then we check if not root, as in we don't have a root node, that is, then return new cell, right? So that will be our root. Otherwise, if strcmp of new cell, that is a cell name, comma root cell name less than 0, right? Then you say root left equal to new cell, right? Else root right equal to new cell. Okay, and then of course we need to return new cell. Now if rt is not a null, then we check if strcmp of rt cell name, comma new cell name is less than or equal to 0, which means that the root is either less than the new cell in terms of cell name or equal to, then we'll go to the right of the tree. Right, so here we'll call make tree, passing in rt, and then rt right and new cell. Otherwise, we call make tree, passing in rt left and new cell. That completes our make tree function. Let's now write code for the print tree function. So void print tree, and the parameter coming in there is struct node *rt. And here we have int calculated as a variable. We check if not rt, meaning if rt is a null, return. Otherwise, print tree passing in rt left. Right? Once we've traversed the left of the tree, remember we're using recursion, so we can print %s, comma, rt, cell name. Right? Then we check if rt formula of 0 is equal to an equal to sign, then we use calculated to get the return value of the function calc formula, which of course is going to take in as argument rt formula. Right? And then we print that formula. So printf %d, and we can leave a tab space, comma, calculated. Right? Else printf %s \t. Remember, we're printing as a string if we do not have an equal to. So rt formula. Right? And after this, of course, we need to call print tree recursively, traversing the right of the tree. So print tree, and our argument will be rt right. Okay, and that completes our print tree function. Now we've got to write the calc formula function. Int calc formula, and parameters will be just one char star fmla. And here we have char sep, comma, operator, and int op1, op2, and result. Now we say here SEP equal to FMLA of 1, right? And then op1 equal to SEP minus 0 to get that integer equivalent. And again, SEP equal to FMLA of 3, right? And op2 equal to SEP minus 0, right? And then operator equal to FMLA of 2. And then of course we check if operator is equal to a plus sign, then result equal to op1 plus op2. Else, if operator equal to a minus sign, then result equal to op1 minus op2. Else, if operator equal to a multiplication sign, then result equal to op1 multiplied by op2, else result equal to op1 divided by op2. And then return result. Right? So this completes the code for all the functions we need. Let's run this code now and see the results. Right, so here we have a typing error or a typo. Let's change that. Print, it should be print F, and that's 98. Now let's put in some input. So let's say D 13, and then say B 11. Remember to stick to single digits, yeah? Right, then we have, let's say, then C, let's say 0 then. Now we don't have a space, so we cannot really make out what's going on here. Let's go back to the code and just make that change. We need to put some space between the cell name and the result or the calculated result, right? So coming to the printf statements that we have here, we can just put in a space, right? So that we have that space before the result. And building that tree again. So now we have A02, which has just a string because we don't have that equal to sign. And of course, the rest are all the results. Right? So I hope that's clear. Now moving on. Write some more code. So write code to locate a node in the tree and to delete a node in the tree. So now let's go back to code blocks and we're going to modify that program. The first thing is, of course, to declare those functions. So right at the top, right? So I'm going to put it after here. You can see struct node star find cell. That is going to be for locating the node. And that's going to take struct node star root and char star key. And then we have another function for deleting the node. So struct node star d tree, and that's going to take struct node star root and char star key. Right, so both these of course are going to be input from the user as to which cell to find and which cell to delete. Right, now within main we will need some variables. So here we will have, in fact you can include it here, we'll have cell to delete, and that will be 4 bytes, and cell to locate. Again 4 bytes, right? And remember, both of these are returning a pointer, so we'll include those as well. So we'll have here, maybe after this, struct node star search for instruct node star search result, or S. Okay. And now within our while loop, or rather after the while loop, that is here, we will have a code block now, and we'll move this statement into that code block. And now we'll ask the user for cell to locate. So printf, enter cell to find or locate. And then of course scanf, %s, comma, cell to locate. Right? And then of course fflash stdin. And then we use search for, right? Or you can use search result equal to find cell, pass in root, and cell to locate. And then check if search result is not a null, then printf found %s, comma, search res, arrow, cell name. Right? Otherwise, printf not found. Okay. The next thing we need to do is ask the user for cell to delete. So printf, you can put in a \n here, enter cell to delete. And scanf %s, comma, cell to delete. Right? And after that, we can use search for to catch the return value of the dtree function. And dtree is going to take root and cell to delete. Right? And remember, after that, we need to say root equal to search for. Now don't forget this statement, right? Remember, because when we are deleting, we would have a new root. So if not search for, then we say tree empty. Otherwise, we call print tree passing in root. Okay. So that completes the changes we had to make in the main function. Now we need to write these functions, that is find cell and delete or dtree. So first of all, struct node star dtree, and that's going to bring in parameters struct node star root and char star key. And within this function, we have struct node star ptr1 and star ptr2. And we check. If not, strcmp of root cell name, comma key, right, which means string compare returned a 0, which means we found a match. Then if root left equal to root right, we can just free root and return null. Else, if root left is equal to null, then I hope you know what to do here. We say ptr1 is equal to root right. Okay, so we save that node or the subtree, and then we free root and return ptr1. Otherwise, if root right is equal to null, then ptr1 is equal to root left, and then free root and return ptr1. So we've taken care of a situation where we could have a left subtree but no right subtree. Otherwise, if we have both subtrees, then we say ptr2 equal to root right and ptr1 equal to root right. And then we have while ptr1 left not equal to null, we go down the tree until we find a null, right? So we just say ptr1 equal to ptr1 left. And when we found that null, we say ptr1 left equal to root left. And then we free root and we return ptr2, right? Now, if we do not find a match, then of course we've got to traverse the tree. So if strcmp of root cell name, comma key less than or equal to 0, then root right equal to d3, passing in the arguments root right, comma key. Else root left equal to d3, passing in root left and key. Right? And then of course we return root. Okay, so this part should have been after that bracket. So you can just Control X and put that here. Why is that? Because this particular bracket is for if we have a match, right? So out of that bracket, of course, we will traverse the tree. Right, so that completes our delete tree function. Next function, or the last function we need to write, is struct node star find cell, and that's going to be struct node star root and char star key. And within this function, we check if not root, then as in if root is null, then return root. Otherwise, while strcmp of root cell name comma key is not equal to 0. And within this while loop, we check if strcmp of root cell name comma key is less than or equal to 0, then root equal to root right. So we traverse the right of the tree, else root equal to root left. Right? And remember, we will exit this while loop if we find a match or if we find a null, which we have to check for. So if not root, break. And then of course, return root. Right, so that completes the find cell function. Let's now run this code. Build a tree first. Now enter cell to locate. Right, so let's say B11, we found B11. Enter cell to delete, let's say C15, and that's deleted, as you can see from the tree printed out. Right? You can play around with this program. Now looking at the analysis of the binary tree approach. The results, as we know with the tree, are much faster in terms of insertion and search times when compared to a linked list. A sequential search, remember, as with a linked list, requires on average n by 2, n being the number of elements divided by 2. That's the number of comparisons we need with the linked list. But with a tree, as we know, we require just log n to the base 2. Again, n is the number of elements. Right? So that many comparisons are what are needed with the binary tree, which of course is less than n by 2. The binary tree approach to sparse arrays is as memory efficient as a doubly linked list. Right? But of course, because we have faster insertions and faster search times, the binary tree approach is better. Are there better alternatives to the tree approach? Yes, there are. And in the next session, we'll talk about the pointer array approach. This completes part 2 for this module. So till the next session, take care, stay safe. Bye.